Hello students and to all my viewers. So in this lecture again I will be solving one more problem based on the cash flow analysis. This problem is taken up from the book of Engineering Economy by D. Garmo, and this is problem number 3.6 unsolved. So the problem is that we have a given cash flow as shown in figure. We have few transactions pointing upwards, that is the cash inflows, and some transaction pointing downwards, that is the cash outflows. So in this we have to find out the value of A as shown in this figure, so that there is an equivalence of cash transactions pointing upwards and downwards. That is, for what value of A the cash inflow is equal to the cash outflow. So let us see how to solve this problem. Let us solve the problem. So what we have is a cash flow, okay, and it starts from 0, 1, 2, 3, 4, 5, 6. So the life of the cash flow is given as 9 years. Of course, these are end of years. We have one transaction, okay, all the representation are in dollars, so I'm just writing this as 400, so dollars is understood. Then there is a transaction of $300, another transaction of $200, and then $100. So these three transactions are there. Now another series, okay, let me choose a different color. So annuities are there starting at the end of 7th year, 8th year, and 9th year. So this is $500 each. And what we have to determine is the magnitude of annuities in the downward direction starting from the end of year 5th, continuing till the last year. So the question is that we have to determine the value of this A, so that the upward and the downward transactions, they are equivalent. Fine. Of course, interest rate is given as 12% per year. So this is the problem. So again, let us see how many different types of series are contained in this one. So let me start with the first series. I'm calling it as A. So forget about the rest. Let me draw. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have a series in which we are having a transaction of $400. So if I call this as the present worth, treating this to be a single payment type of transaction, so P1 is given as $400. So this is given P1. Okay, let it be A1. Now another series is, let me call this as A2. So what I am doing, I am splitting this series into a standard series. So the first series is that we have a single transaction of $400 magnitude, which is at n equal to 0 or t equal to 0. Another series, okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have a series in which the first transaction is 300, then 200, and then 100. Fine. So although it seems it is a gradient series, but an inverse gradient series. For a standard gradient series, the series should be such that it increases as we move from 1 year towards the end of the cash flow. So what I can do, I can manipulate this series in this way so that the standard relationship that are available for the gradient series, I can directly apply those relationships. How I can do that? If I just draw a line here and I extend it to 300. So what I have done here, 200, but I am extending it, so 100 I have added here. So in order to nullify this effect, I can simply subtract whatever I has added, 100. And here, since it is given as $100, so in order to make it at a uniform series, 200 is added to this to make it 300. So to nullify the effect of $200, I am adding a transaction in the opposite direction. Fine. Now if I see this again, in this I have now two series. What are they? Okay, 0, 1, 2, 3, 4, 5, okay, to 9. So we have 300, 300, and 300. So this is $300. Now another series, 0, 1, 2, 3, 4, so on up to 9. And I have one transaction here of $100 and another transaction here of $200. Now if I just compare, this is nothing but this is a uniform series. Or what we call as annuity. And this is a standard gradient series where we have G equal to 100. Now, if I solve this one, the uniform series, so let me, okay, so now I am solving for the uniform series. So if I know the relationship, what I am interested in, I am interested in finding out the equivalent worth of these three transactions, that is the annuities at this point of time. So let me call this as P2. So because this is a standard series, so I can use the result or directly the result, that is P relationship between PA and A is P equal to A 1 plus I to the power n minus 1 upon I 1 plus I to the power n. So A is given as 300. So if I call it as this as P2, so P2 I can evaluate simply by putting A equal to 300. 1 plus I, so I am directly writing I is 12, so it will be 1.12 to the power n. N is how much? 1, 2, 3. 1, 2, 3. So it is 3 minus 1 upon 0.12 into 1.12 to the power 3. So if I compute this numerical value, this comes out to be 222.075, of course in dollars. So this is P2. So presently I am just focusing on the cash flow, on the upward cash flow, that is the cash inflows I am considering. So this is P2. So this is P2. Now this is a gradient series. Let me call this as, okay, let me call the equivalent of this gradient at this point of time. Let me call this as P3. So this is a standard gradient series. If we see, there is no transaction at the end of year 1. The first transaction is taking place at the end of year at the end of year 2, and G here is 100. So if I just apply the formula between the present worth and the gradient series, P is G bracket 1 plus I to the power n. So smaller n, sometimes I am using a small sum, this is my fault. So this is all same. Oh, let me put it capital N, minus I n minus 1 over I square 1 plus I to the power n. So if I just fill up the numerical value to find out what will be the value of P3. So P3 is equal to, G is given as 100 bracket 1 plus I 1.12. Now I here is 1, 2, 3. So this will be 3 minus I is given as 0.12 into 3. Okay, this is close, minus 1 bracket close over I is given as 0.12 to the power 2 and 1.12 to the power 3. If I compute the numerical value of this, P3 comes out to be $. Okay. So P3 comes out to be $222.075. So this is basically, I have not written it correctly. If I just compute this value, this is coming out to be $720.549. So this is coming out to be $222.075 when I calculated the equivalence of this gradient at this point of time, and this is the equivalence of the uniform series at the present point, that is at t equal to 0 or the beginning of year 1. Now another series what we have, so these three series we have already taken up. So A2, there are two components. One is the uniform series, another one is a gradient series. Now what else we have? We have another series of $500 each, and this is again annuity. So another series. So let me draw A3. Okay, let me use a different color. So A3, okay, 0, 1, 2, 3, 4, 5, 6. So what we have? We have 3 transactions of $500 each. Now, as we did earlier, if I want to use the standard for relationship between P and A, and PA is given, I am interested in finding out P. It will be evaluated not at 0 but rather at n equal to 6. So let me denote this as, so if I am interested in calculating the equivalence of this series at this point of time, and I am calling this as P4 dash. So again, the same formula, the relationship between P and A, what we have used here. So if I just put up the numerical values, P4 dash will be equal to A is 500, bracket 1 plus I, 1.12. Now if I count the number of years, 1, 2, 3. So it will be again 3 minus 1 over 0.12 into 1.12 to the power 3. So the numerical value for this comes out to be $1,200.915. So this is the value for this series. Now this is P4, and this P4 is nothing but this is the equivalence of this uniform series at n equal to 6. But what we are doing, we are calculating the equivalence at n equal to 0 or t equal to 0. So if I treat this P4 as future worth, and I can apply the relationship between P and F to compute the equivalence of this P4 dash at point or at time t equal to 0. So let me call this as, say, P4. So if I just use the relationship between P and F, I can find out what will be the value of P4. So the value of P4 will be equal to P4 dash upon 1 plus I to the power n. So P4 dash 1200915.915, okay, and 1 plus I, so it will be 1.12. Now n, 1, 2, 3, 4, 5, 6, n will be 6. So this comes out to be 608.421. So if I just find out what is the net worth for cash inflows. So P net, this I can write down P1, okay, then P2, the direction for P1 and P2 remains the same. but as far as P3 is concerned, it is in the downward direction, so I add it with a negative sign, P3, and finally P4. So if I just add all these values, so this will be 400 plus P2 is coming out to be 720.549 minus P3 is coming out to be 222.075, and finally P4 is 608.421. So if I compute, this comes out to be, this comes out to be $1506.895. So this is the net worth, or I can say this is the net cash inflows at n equal to 0 or t equal to 0, that is at the beginning point of time. Now we have, so let me choose another. Okay, so what we have another series, what we call as cash outflow, and we have to compute the value of this A. So if I am interested in finding out what is the equivalence of these transactions, as this is a uniform series, I can use the standard relations available to find out the equivalence of these transactions. Say the amount of each transaction is A, and I can find out what is the equivalence of all these transactions at this point of time. Let me call this as PB. Now the relationship we all know, that is P equal to A. Let me write it once again, 1 plus I to the power n minus 1 upon I 1 plus I to the power n. So if I find out the value of PB in terms of A, it will be PB A 1 plus I, so 1.12 to the power n, 1, 2, 3, 4, 5. So it will be 5 minus 1 upon 0.12 and 1.12 to the power 5. So if I compute this, PB comes out to be $2.2909A. But in the previous section, what we have calculated the equivalence of all these transactions at this point of time. So we have calculated at this point of time. So we have already discussed that the value should be same at the same point of time in order to have equivalence of the two cash flows. Now PB we have calculated at n equal to 4. So I can treat this PB as future worth and find out what is the equivalence of this PB at this point of time, that is at n equal to 0. Let me call this as, okay, PB net, any name we can use. So PB net PB net, this we can compute by F upon 1 plus I to the power n, where F is given as 2.2909A upon 1.12. Now for the number of years, 1, 2, 3, 4. So this comes out to be, Okay, so this comes out to be 2.2909 A, and this I have not written correctly. This is coming out to be dollar 3.604 A. So this will be dollar 3.604 A. So this is PB net. Now for equivalence, what we have is PB net upwards, P net upwards, P net should be equal to PB net, that is the upward cash flow must be the same as the downward cash flow. So if I just equate, it will be 2.2909 A equal to what we have computed earlier, 1506 point, let me check what is the numerical values, 06895. okay, 06895. So if I find out, A comes out to be 5657.77, of course, dollars. So this will be the value of this A, so that the upward and the downward transactions, they are the same. So this is the solution of the problem. So this is all how we solve problems pertaining to equivalence of cash flow, and as many problems as you can solve. We have many problems at the end of the chapter on the time value of money. So on similar lines, these problems can be solved. I hope this will give you an insight of how equivalence of cash flows can be taken up and how the numerical problems based on this topic are solved. So once again, thank you very much. Thank you for a very patient hearing of this lecture. Have a good day. Thank you very much.